Hello, my name's John Green. I'm a final year PhD student at the University of Edinburgh. I'm working under the supervision of Jim Wright, and I'm expecting to graduate in the middle of 2022. I'm mainly interested in harmonic analysis, particularly oscillatory integrals and problems in harmonic analysis possessing a geometric flavour. And I'm currently on the market for postdoc positions starting in mid to late 2022, around September. In this talk, I plan to give a fairly gentle survey of some of the results of my research from this past year. But before moving on, I'd just like to thank the organisers for the opportunity to give this short talk. I think this is a very nice way to connect with the mathematical community during these difficult times. Okay, so here's a list of my publications and preprints. What I'll be talking about today can mostly be found in these latter two preprints and the references therein, so I'll avoid making too many explicit references to where everything's from. You can just refer to those. But I will also include in this talk some small modifications to some of the results in the first preprint that I have not yet incorporated. Now, broadly speaking, I've mainly been thinking about the relation between oscillatory integral estimates and sublevel set estimates. So first, let's recap some terminology of what these are. So an oscillatory integral has a phase function f, and we have a frequency parameter lambda, and then looking at this expression below, we have e to the I lambda fx representing some oscillation with phase f at a frequency lambda. And we also have an amplitude function eta, which is important but typically less interesting. Mainly we're interested in the dependence on f. And then we have this object I of lambda. I won't write eta and f in part of this notation. Lambda's all I'll write, but know that the dependence on eta and f is important. And typically what we're interested in is bounding the decay rate at infinity of this object I of lambda. So for the purposes of this talk, as I said, eta is not so important. We'll generally just take it to be identically 1. Also, the sublevel set at height c and width epsilon for a real valued function is this. S of epsilon and c is this set where f is at most epsilon away from c. Okay, so then we'll typically try to estimate these sublevel sets as a decay rate as epsilon goes to 0. And so it's known that these are quite strongly related. The intuition for these objects kind of gives it away a bit. So we expect that as we increase the frequency lambda, then provided f is not approximately constant, provided it moves around a lot, then increasing this frequency will increase how much this oscillation occurs. And so when we take the integral, there's going to be lots of cancellation, and this is going to become smaller and smaller as we increase the frequency, provided f doesn't move around, f does move around a lot. And so saying that these sublevel sets are small is kind of one interpretation of what it means for f to move around a lot. Okay, so here's a well-known result saying that oscillatory integral estimates imply sublevel set estimates in many cases. So we take some finite measure space, we take some delta between 0 and 1, which might be called the decay exponent. We have some measurable function, and suppose we have these oscillatory integral estimates. So for each frequency lambda, we have this decay. Then for each height c, we have this bound on the sublevel set estimate. And so it's important to note here that there's a kind of uniformity. So if we replace f with some other phase satisfying the same estimates, then for that phase we'll also get the same sublevel set estimates. There's uniformity there. And that's an important property that we'll want in the results that I'm going to talk about in a moment. So the results I'm going to talk about are going to be about going the other way. So notice that this is a very general statement, and the proof's fairly straightforward. I won't go into it, but you can find it in the references I've listed. And I also want to stress that these estimates possess only measure theoretic properties. It doesn't matter whether f is, say, a smooth function or not, although that will be in practice important for establishing such estimates. But all that matters is measure theoretic properties of the phase. And the reason why this is important to note is that later we're going to exploit this by saying, well, if measure theoretic properties are all that matter, then these estimates are invariant under rearrangements of the phase. And we'll come back to that later. Okay, so I'm interested in proving oscillatory integral estimates from sublevel set estimates. And the philosophy of how I'm going to do that is I want to do this under some geometric, qualitative, structural assumptions on the phase. So what do I mean by that? Well, let's look at an easy example. Here's a one-dimensional result. So suppose we have a phase function on some interval, and it satisfies this condition that the nth derivative is single-signed for some n bigger than or equal to 2. So for n equals 2, that's convexity. In general, we can think of this as a higher order convexity condition. And let's now suppose that we have these sublevel set estimates. So we have that each sublevel set with epsilon is bounded by t of epsilon for some strictly increasing, strictly concave function t, with t of 0 equals 0. This isn't too much of a restriction in one dimension. So let's not worry about why I've done this at the moment. Then this oscillatory integral is bounded by some absolute constant times capital N times t of 1 over lambda, which is the behaviour we expect to see. We can see in some sense that the result on the previous slide is sharp, so this is kind of a fairly strong reversal of it, subject to this assumption in this special case. Okay, so how does the proof of this go? It's relatively simple. Because this nth derivative is single-signed, given any positive epsilon naught, we can partition the interval from a to b into at most n-1 intervals where the first derivative is small, and n intervals where it's large and monotone. Then for each of these latter intervals, we can bound it by some constant times epsilon naught lambda to the -1. This is just van der Corput's lemma, or a simple integration by parts argument. Now for the former intervals, we can say pick some interval I, pick some point y in that interval, and note that for any other x in that interval, the difference between f of x and f of y is at most epsilon naught, because that's what the derivative is bounded by on that interval, times the width of that interval. So that's just the mean value theorem. And then we have this set inclusion that that interval is in this sublevel set at height f of y. So we get this bound on the width of I. And then using some of the properties of T we can rearrange this for a bound on the width of I. And then we have that estimate on the width of I and this other estimate here, and we can optimize in epsilon naught, and note that because there's n of these intervals we multiply by n, and optimizing this choice is going to give the result from the previous slide. Now, by modifying this proof slightly, in one of my preprints I considered the behavior under composition of the phase with a polynomial or some other function possessing nice structural properties, but I'm not going to talk about that in this talk, just in case anyone's interested to go and read that. That's just something to mention. Instead, I'm going to be looking at the higher dimensional case of this result, but it's quite hard to know what the generalization of this assumption should be. And in the first instance, one might consider the nicest convexity / geometric assumption available, which is of course convexity. So that's what we'll do. So suppose we have some convex phase with a single minimum, a single critical point, which by multiplying the oscillatory integral by a constant, just to translate that phase, we can assume it to be 0. And we want to obtain estimates like this: bounds on the oscillatory integral by some constant times the measure of this correct sublevel set. I should stress at this point that the main contribution for an oscillatory integral comes from the critical points, so this is quite natural to only look at this single height. Now, under certain quantitative hypotheses, results like this have been obtained before, such as in the work of Brunner, Nagel and Wenger, where their assumption is essentially that the restriction of the phase to lines does not vanish to infinite order. We're going to be interested in qualitative hypotheses though, and I should mention here that it is necessary that an additional hypothesis than convexity be imposed. There are counterexamples to this kind of estimate, even in the radial case otherwise, unless we're in dimension 1. Okay, so now here's a result I've proven in the other preprint. So let's look at the restriction of f to some sublevel set of height L. And suppose that between 0 and L, the measure of the sublevel set as a function of y, as a function of height, as a function of width, is a concave function. Then we have this estimate. The oscillatory integral with amplitude identically 1 is bounded by an absolute constant times the dimension times this sublevel set. And here I've got omega n to the minus 1 over n. This is just the volume of the unit ball in Rn to the minus 1 over n, divided by lambda. So this is the natural kind of estimate to look for. I've not stated the result in the most general way possible here, but I think it's more interesting to understand some of the ideas going into the proof. So I'll just give a quick sketch of that now. So by the co-area formula, we can write the integral like this. And I'm going to write this inner integrand here as j of s. Then we can split the integral into two parts and use trivial estimates on one part to estimate by this sublevel set. And for the other part, we can use a simple integration by parts argument and the assumption, which is equivalent to j being decreasing, to bound by j of epsilon naught. And then to estimate by j of epsilon naught, we can use an equivalent formulation of j of epsilon naught, where f is replaced by its Schwarz symmetrization, a non-decreasing radial rearrangement. The important feature of this is that in order to generalize the step from the previous argument, where we used the fact that we can bound the difference between two values of f in terms of the diameter, here we need to be able to relate the diameter to the measure, which we can do in the radial case. And then we also use the fact that the sublevel set is related to the level set in the radial case, since the level sets are just spheres. And so these two things together give us an estimate on j of epsilon naught, and using similar arguments to before, we can optimize the two estimates and get the desired bound. For the details of that, please look at the preprint if you're interested. Okay, and finally, I'm just going to give some equivalent conditions to this concavity assumption that I mentioned before, just so you have something of a feel for what these assumptions actually mean. So in general, it takes this form, which is quite complicated. So here we have the gradient appearing, the Laplacian, and this h of f is the Hessian. But in the radial setting, it can just be rewritten as this, which might be a bit easier to get your head around at first. And that's really all I wanted to say about those particular results. So thank you for your attention. I've listed my email here, which you're welcome to contact me at if you have any questions about anything I've spoken about today. And other than that, thanks for watching.